Okay, let's do some examples, and here's the first one I want to look at, one where it's one of our differential equations that we've been looking at, second order linear homogeneous constant coefficients. The coefficients are chosen to all be 1 here. So 1 for A, 1 for B, 1 for C. And this is a full initial value problem. So we have a differential equation and some initial conditions. There should be a unique solution. So final answer, I want x of t equals and then some function of t with no other parameters in it. It would just be a function of t. All right, so first thing I do is guess e to the lambda t, right? And after I make that guess, I end up with a characteristic polynomial. Lambda squared plus lambda plus 1 equals 0. So now I need to know the roots of this polynomial. And if I can factor it, great. But if I cannot factor it, then the quadratic formula can be used. So to find the roots, let's see, negative that thing plus or minus square root that thing squared minus 4 times this thing all over 2 times that thing. So bunch of 1s. Okay, so negative 1 plus or minus the square root of 1 minus 4, so negative 3, all over 2. This is a complex roots situation. And of course I knew that before I started doing the problem. That's why I chose it, because I want to show you an example of this complex roots situation. So the two roots that I got, so let me clean this up a little bit. I've got negative 1/2 plus or minus negative 1/2, or if you want we can say minus plus 1/2 square root negative 3. Now square root negative 3, these kinds of things can be written like this in order to figure out what are the complex roots of this polynomial, which has no real roots. So normally, if you had not studied complex numbers before, then once you reach this stage, you would say, the quadratic formula is pooping out nonsense here, right? It's giving me total nonsense. Therefore, there are no roots. This polynomial has no roots. If you were to plot it, it would be like a picture of a parabola floating above the axis. It does not cross the axis anywhere. So there are no roots. However, now that we are allowing ourselves to use complex numbers, a manipulation like this is a way of figuring out what are the complex roots. So this is plus or minus, it doesn't matter if I write plus or minus, minus plus, 1/2 I times root 3. Maybe a cleaner way of writing it is minus 1/2 plus or minus root 3 over 2 I. So real part negative 1/2, imaginary part positive or negative square root 3 over 2. Great, so I am in case 3. And remember, we saw that in case 3, we only need one of the two roots. So it's enough to just focus on, say, the one with a plus. That's sufficient. So let me write that properly. Negative 1/2 plus root 3 over 2 I. Okay, so that's good enough. And this all arose from the guess e to the lambda t, right? And we have found that lambda equals this thing. So e to this complex number times t is going to be a solution. But it's a complex solution. How do I get to a real solution? And here's the answer. First write it like this. Then this will help you to figure out what are the real and imaginary parts. Then pick them off and you will get two linearly independent real solutions. So picking off the real and imaginary parts, let's see. First I need to write this in terms of real and imaginary parts. So I get cosine root 3 over 2 t plus I sine root 3 over 2 t. So you see in our complex solution, you see the different roles played by the real and imaginary part. They do very different things. The real part seems to appear here as like an exponential growth or decay rate. So that's what the real part does. And the imaginary part seems to appear here playing the role of like a frequency kind of thing, called an angular frequency. So when the real parts that come out are exponential growth or decay rates. The imaginary parts that come out of your characteristic polynomial roots are more like oscillation frequency. All right, so this is e to the negative t over 2 cosine root 3 over 2t plus I e to the negative t over 2 times the sine of root 3 over 2t. So now pick off the real and imaginary parts, and there's two linearly independent real solutions. So x1 of t equals that. There's one nice real solution. And x2 of t equals that. There's another nice real solution. You see, I'm ignoring the I. I'm taking the imaginary part. So these are two nice real independent solutions. So here's the general solution then. It's c1 times this plus c2 times that. Let me just copy and paste here. There. There's my general solution. So that is what I'll call x of t. Now, let's go back to the original problem. The original problem was actually an initial value problem. It had x of 0 equals 0 and x prime of 0 equals 1. So let's impose those initial conditions and see what that looks like. There's nothing too interesting going on here, so maybe skip ahead in the video if you're bored and you know how to satisfy initial conditions. At the end of the video, I'll show some plots and stuff. Okay, so let's see. X of 0 equals 0. To impose this initial condition, I need to plug in t equals 0. If I plug in t equals 0, then I get, so the right-hand side of this equation is 0, and the left-hand side is what I get when I plug in t equals 0. And I can already tell you that this term is going to die because it's going to be sine of 0, which is 0. The term on the left side, though, if I plug in t equals 0, then cosine of 0 is 1, and e to the 0 is 1, so I just get c1. Okay, so that is a nice initial condition, x of 0 equals 0. That initial condition kills off a whole term here. So now I'm left with x of t equals c2 e to the minus t over 2, like that. And now I'm going to impose the initial condition x prime of 0 equals 1. To impose this, I need x prime, so first I need to take the derivative of this to get x prime of t. Now there's going to be a product rule, so x prime of t, and by the way, notice that I'm lucky that I chose an initial condition here that kills the first term. Not lucky, actually. I chose it because I'm lazy and I didn't want to do such a long example. But if my first initial condition were x of 0 equals something more complicated, then I would have gotten something different here, not c1 equals 0. And then here I would have still had two terms to deal with. Then when I take a derivative, there'll be a product rule for each of those two terms. So I'll have 4 total terms to deal with in my derivative. So that would be annoying. Okay, but here I just have 2 terms coming out of the one product rule. So I've got c, let's see. So first the derivative hits this factor, and then the derivative hits this factor. When the derivative hits this first factor, I get negative c2 t over 2, I'm sorry, negative c2 over 2 e to the minus t over 2 sine root 3 over 2t, plus, now when the derivative hits the second factor, I get root 3 over 2 coming out. So root 3 c2 over 2 e to the minus t over 2 cosine root 3 over 2t. All right. Then now I can finally impose this equation. So I want 1 to equal the thing on the left-hand side here. So what I get when I plug in t equals 0 in for x prime here. So when I plug in t equals 0, what do I get? Well, this first term actually dies because it'll be sine of 0. The second term, I get 1 for this and 1 for this. So I just get root 3 over 2 c2 yeah, that's it, equals 1. Yeah, I think that's right. So then C2 is going to be 2 over root 3. Nice. So now I've got my particular solution. My particular solution is my general solution up here. So let me just copy and paste my general solution and then replace the coefficients. So there's my general solution. Then I got C1 equals 0, so I don't even need that whole term. And C2 equals 2 over root 3. All right, so there's my solution to the original initial value problem. So this is my solution to the original initial value problem, which was this. Okay, so let's plot it just for fun. So here I'm going to say plot 2 over root 3, then the exponential of minus t over 2 times the sine of root 3 over 2t. And let's plot it from t equals 0 to t equals 3, I don't know. And let's make the plot run from negative 1 to 1. Okay, so there we are. So the horizontal is time, and vertical is the output at x of t. The vertical is x. And let's look at the plot and see if we believe the initial conditions are satisfied. So the initial conditions were x of 0 equals 0 and x prime of 0 equals 1. So those initial conditions were putting demands on the value of x at t equals 0. So and the derivative of x at t equals 0. So x of 0 equals 0 tells us that when time is 0, so when time is here, the value of x should be 0. So it should be there. Okay, good. So the graph passes through 0, 0. The second initial condition is telling us about the slope of this graph. It's saying x prime of 0 should be 1. So here we should have a slope of 1. And indeed we do. The time axis now is on the same scale as the x-axis. So a slope of 1 literally means that the tangent line here should be a perfect 45-degree diagonal, and that looks plausible that is, just visually. So that's good. The slope here looks like it's 1. If my second initial condition were like 20, x prime of 0 equals 20 here, then I would expect this to be very steep. All right, so you see what the initial conditions are doing? They're starting off where this should start, and then how steeply it should start. So that's what you're prescribing when you say the initial conditions. Now let's let this run for longer. What's it going to do? It looks like it goes up and down. What if I run it for time up to 10? It goes up, down, comes back up. Time equals 20. Okay, so it decays pretty quickly. The amplitude decays pretty quickly, but you're getting oscillations just with a decaying amplitude. So it's going to go up, down, up, down, up, down, up, down, up, down, up, down, but with decaying amplitude. So if I were to zoom in on one of these regions, I would see it still kind of going up and down, but just with very low amplitude. And hopefully that makes sense when you look at this. If I were to leave out this portion, let's say I didn't have this part, then what is this? It's just a sinusoidal function, right? It's just going to look like it's oscillating with a certain frequency, right, or with a certain period, which is determined somehow by this number. Including this now, so yeah, sorry. Okay, without this, you just have a sinusoidal function, right? It's oscillating, and the frequency somehow is related to this number, and the amplitude is this number. So the minimum and maximum values that sine takes on are -1 and 1. So as time goes on, the sine function here bounces between -1 and 1. If you multiply by 2 over root 3 and then let time run forward, then you'll see this overall bouncing between negative 2 root 3 and positive 2 root 3. So this is the amplitude of oscillation. Now if we include this part, then as time goes on, your amplitude, you can think of this as your amplitude. As time goes on, the amplitude decays. So it's kind of like this is x, this is t. It's kind of like you have this exponential, this is the picture of exponential decay. And what I'm doing here is I'm drawing kind of a mirrored, like here's the exponential e to the minus t over 2, and then here's a mirrored version of it. So I'm showing you plus and minus this amplitude function. So it's like the amplitude is changing in time. And then here you've got your oscillation, and the amplitude is changing in time. So it's sort of trapped between these two, and the amplitude is decaying in time. So think of this as oscillation with decaying amplitude rather than constant amplitude. It's kind of interesting. One thing to notice is that it's not, is the frequency is the same all the time. So where these zeros are appearing in the graph, where these zeros are, they're always spaced the same. Although my drawing is not so good, but the zeros are supposed to be spaced the same. So the gaps between successive zeros here are always the same. They're not shrinking. For some reason my drawing shows them as shrinking, but the gaps should always be the same. Yeah, maybe if I make this plot range smaller, it'll be more visible. Yeah, I don't know. So the gap from here to there is the same as the gap from here to there, is the same as the gap from here to there, is the same as the gap from here to there, and then it's kind of hard to see from there, but that's the idea. So just briefly, since these are coming up a lot, let's discuss what is the actual frequency. What is the size of those gaps? Can we figure that out from here? So like if I give you sine of omega t, a sine omega t, then the plot of that will be something like this, right? And if I throw in exponential decay, then it'll actually decay over time. But let's just focus on this. How do we interpret the omega part? So this part is called angular frequency, which is a little bit different from frequency. So the way I like to interpret angular frequency is I think about the periodicity of sine in the first place. Sine repeats itself every 2 pi radians, right? So the sine function, if I take the sine of one number plus 2 pi, then I get the sine of the original number. So every time you add 2 pi, the sine repeats itself. So what would I have to add to t? How many units of time would I have to add to get the sine to repeat itself? Well, if I add 2 pi over omega units of time to t, then I get, when I distribute, the omegas cancel and I get sine of omega t plus 2 pi, which is sine of omega t. So the sine function, sine of t, repeats itself every 2 pi. Sine of omega t repeats itself every 2 pi over omega. So the period of sine omega t, or a sine omega t, meaning the time it takes to repeat, to do one cycle and then start to repeat, is going to be 2 pi over omega. So given a sine omega t, the period is 2 pi over omega. This is in units of time. So let's just put a specific unit. It doesn't matter what it is, but let's just say t is in seconds, then the period is this many seconds. Then this angular frequency also has units. So whenever something's going into a sine, then it has units of radians. So overall, this thing has units of radians, right? Then the units of omega by itself, if I take the units of omega by itself, if the units are going to work out here, omega must have units of something that when I multiply it by units of seconds gives me radians. So it has to have units of radians per second. So that's the units of the angular frequency. So usually when you're in case 3 with these kinds of differential equations, when you get your imaginary part beta here, that's something that has units of radians per unit time. That's usually the way it goes. And the actual frequency is not radians per second, but is cycles per second. So something which is how many repeats, if this is time, given 1 unit of time, how many periods occur, how many repeats occur. So period you can think of as seconds per cycle, right? If you want to get if you know how many seconds are in a cycle and you want how many cycles are in a second, we'll just take the reciprocal. So 1 over the period is the frequency. So this is how many cycles are in a second. So this is why I'm not referring to omega as a frequency, I'm referring to it as an angular frequency. Omega is angular frequency with units of radians per second. It's how many radians there are in a second, while actual frequency is how many cycles there are in a second. Another way to think about the relationship is you can directly convert between omega and frequency like this. So if you have omega cycles per second, then, and you want something, I'm sorry, omega is in radians per second. If you have omega radians per second, and you want to get something like a frequency in cycles per second, then you need to multiply, for your unit conversion, you need to multiply by how many cycles there are in a radian, right? Well, that's a little bit weird, cycles in a radian. But you know how many radians there are in a cycle, right? How many radians take you around a circle is 2 pi. 2 pi radians for 1 cycle. So omega over 2 pi is how many cycles there are per second. So that's the relationship between omega and actual frequency. So that means in our example back here, the size of the gaps, not exactly these gaps, but the period gaps, so 2 of the gaps I was drawing, the size of the gaps I have here is going to be this thing. This is our angular frequency over 2 pi. Sorry, 2 pi over the angular frequency. So that's the period. So that's the size of these jumps here. So our period is 2 pi divided by square root 3 over 2. So times 2 over square root 3. So going back here in Mathematica, let's see if we can observe that actually being the case. So what if I make my t run from 0 out to whatever that number is? Oh, sorry. What if I make my t run out from 0 to whatever instead of out from 0 seconds to 20 seconds, I'll make it run from 0 seconds to this many seconds. So first, let's approximate what that number is. I'm just curious. 2 pi 2 over root 3. This n function does a numerical approximation of the number, so it gives me something in decimals. So it's about 7.25. Okay, interesting. So if I run this to about 7.25, and let me just let the plot range be automatically chosen. Yeah, see? That's how long it takes for it to do one up and down and come back. Now, I wouldn't say that that's the actual period of this, because this is technically not periodic, since the amplitude is changing in time. One cycle is not going to look like the next cycle, right? But you can still kind of call it a sort of period. Okay, so the lesson I want you to take from this is that whenever you're in case 3, once you get your root of your characteristic polynomial and you see that it's complex, you immediately have a way of thinking about what you got. You can think of the alpha part as an exponential growth or decay rate. That depends on whether it's negative or positive. In our case, our alpha was, where is it? In our case, our alpha was negative 1/2, right? Way back here when we were working out our root of the characteristic polynomial, it was negative 1/2. So we ended up with exponential decay. And you can think of the beta that you get here as an angular frequency. So something in radians per unit time.